Actually, it's 7 o'clock right now, so I will officially start. And so I'm going to answer any questions you have. Like it says at the bottom of the screen, you could either put it in any questions you have or answers or whatever in the YouTube chat, or in the Remind app is fine by me. So let's see. All right, so the Unit 7 test is on Tuesday. Today is Sunday. So if you're watching this not live, then that's part of the reason that I want to do this tonight, is to give you an opportunity to review this, because I know not everybody can make the live streams, no matter what day I choose to do this, and I'm able to do this because honestly, I'm doing this also tonight because tomorrow is a little bit not as good for me. So circuits and Ohm's law, there's two standards for this unit. And the first has to do with just the basics of circuitry, and getting a little bit kind of sort of into parallel versus series, and that's about it. So a little bit more also to just like how things work. For example, you have to know, let me start over. You can think about this question, but as you are struggling and persevering with trying to figure out those combination circuits, don't forget to go back and review this kind of stuff. I'd hate for you to get a question wrong because you're just not 100% sure and you're second guessing yourself because you spent 90% of your time working on a concept that's going to have like 2 or 4 questions. You know what I mean? So the combination circuits are important. They are on the test. It won't be like the big ugly from the quiz, maybe not that complicated, but they are on there. But there's going to be a lot of other stuff on there too. For example, the flow of electrons. Hopefully, you know the name of this one. Let's see. I gotta get my. It's been a little bit since I did this. So pen. There we go. Flow of electrons. These things all sound good. They all sound like they're related, and they are. But the actual flow of electrons is called current. Okay, it's the flow of the charges. The flow of the charges. In physics, we refer to those charges as electrons. I told you that if you get into electrical engineering and electrical work, things are a little bit backwards, different, because electricity was discovered before electrons were discovered. So, yep, you are correct with A. A is, okay, so like I said, this is the kind of stuff that it's good to know, because the simple stuff is easy to get. You don't want to get this stuff wrong. Okay, what does a battery or other power source provide to the circuit? You will be expected to have to draw or describe the battery. Remember that one quiz question? There was a quiz question a couple weeks ago before spring break. I asked you to describe what a battery does. You're going to have to do that again. I think I even told you you're going to have to do that on the test. So be ready for that. What do you call it? Multiple choice style question, because don't forget there are FRQs. And you know, FRQ is a great place for me to ask you to describe in your own words how does a battery work, and draw pictures and all that good stuff. So be ready for that. However, multiple choice. What does a battery or power supply, that thing, provide to the circuit? And you start second guessing yourself on this one, right? You're like, ooh, I think I know what it is. I think I know. But there's some, ooh, maybe it could be this, could be that. But the answer is, when it comes down to it, voltage. It provides the voltage. It provides the push, okay? The push, the pressure. I'll put push or pressure, all right? And that's what causes the current, okay? Without the push, without the pressure, the electrons, the charges won't flow. You won't get that flow. You won't get that current. So you might have been second guessing yourself. Wait a minute. Does it provide current? Nope. And ohms, we can argue about ohms. There's always internal resistance in a battery. But primarily, the purpose of a battery or a power supply is to provide the push, the voltage. All right, electric potential, energy, basically. Okay? All right, so again, don't forget the basics. don't get confused about this. Don't second guess yourself. Okay. It's okay. Well, it's okay to second guess, but only to make sure, right? Don't overthink it. So here's a little animation that I like to find on the internet, and they're never quite perfect. So these are just basically analogies. So here's your circuit or your battery with the rest of the circuit, and without this pressure, these electrons, these charges will not move. So that's what causes it. It does not. Here's the common misconception is that it provides all these electrons. Like it's just a jam-packed, pressurized can of charges, electrons, just waiting to be released, like a shaken up can of pop. But it's not. That's not what they do. The electrons are already there. If you remember the FET simulation you did, the electrons are already in the wires. The charges are already in the components, in the light bulbs, in the resistors. So it's one popular choice is that it provides the charges. So it would be F. That would be incorrect. It does not provide the charges. Okay. It does not provide the charges. It provides the voltage, the push. Okay. You notice I'm not doing the polling this time. I feel like that just didn't quite work. If I ever, I'm still looking on ways to make this a little bit more interactive. Since you're not able to log in as well, anyway, that's a whole other story. All right. For electrical current to flow, which of these are necessary? I have a question. What does charging a battery do? Oh, that's a fantastic question. Okay, because the word charging gets a little confusing if you start thinking in terms of like positive and negative charge. It's not the same thing. It's like recharging a battery. All right, there's a reminder for me to do something. And yes, that's my reminder tone. Okay, charging a battery, recharging a battery. This action here, this pushing, this voltage is caused by that. I think I drew it on the board. There's like a battery, and if you remember, so here's the positive side. And I basically said that there's like a chemical reaction happening inside here. I drew it marginally better on the board because I did it slightly slower. And that forces all these electrons to one side so that you get a positive side that is missing all those electrons. All those electrons that used to be here are now pushed over to the negative side. So recharging or charging a battery, basically, it undoes this chemical reaction. So when you buy a battery, when you get a battery and it's fresh, basically you could think of it simply as there's two parts of a reaction just waiting to react. It's sort of like you have baking soda and vinegar. It's not, those aren't the chemicals that are in there, but you could think of it. Those, if you've ever mixed baking soda, if you've ever done a volcano, you mix baking soda and vinegar. You mix them together, what happens? It doesn't quite explode, but it gets a lot foamy. You put some soap in there, it's, get the whole volcano, some red dye. So when you do that, you no longer have baking soda or vinegar. You get a chemical, like you get a combination of both. It changes it. It changes them both fundamentally, or chemically anyway. You'll learn more about this in chemistry. And in a standard battery, unrechargeable, that is an unreversible reaction. You cannot do something to separate out the baking soda from the vinegar again. But in a rechargeable battery, you can. And then, so when you buy it from the store, you get like, it is basically part of one chemical, part of another chemical. And as you use the battery, those chemicals slowly start to come together and mix and create their the chemical reaction that pushes the electrons to one side. And so I'm repeating myself, but in a non-rechargeable battery, that's a one-way street. In a rechargeable battery, you can slowly undo that. So that's what happens when you charge your battery. You're undoing the chemical reaction. You are providing energy. It's the opposite. Instead of getting energy out of it, you are providing energy to put it to separate them apart. So that's the quick unchemical answer to that question, which is a phenomenal question. All right. And that will not be on the test. So just to be clear, you'll have to be able to like explain how that works and all that, but the whole process of charging a battery and recharging it, rechargeable batteries is a little bit beyond us right now. All right, cool. Great question. I'm looking on remind, nothing there. 4, electrical current to flow. Which of these are necessary? Choose more than one. Okay. Just give you a second to think this through. You don't have to put it in the chat because honestly, there's a delay, unfortunately, that I can't get over. And I start talking and then I see all the answers pop up. So that's what happens sometimes. So do you need a conductor? Well, for current to flow, it needs something in which to flow. So yes, you need a conductor. Okay. You need something through which the charges can flow. Do you need amperage? No, that is the unit of measurement of flow of current. So you don't need it. That's like saying I need inches when I'm, I don't know, ordering Subway. It doesn't really make sense. Resistance. No, you don't need that. In fact, not typically, but oftentimes you don't want that because it just causes problems and heat and stuff like that. So oftentimes it's good because you don't want a full blast current going through either. You do need voltage. You need that push. Okay. So in order to get currents to flow, you need a push and you need something through which the pushed charges can flow. Okay. Oh, that's right. D is correct. See, I am checking my remind. And by the way, remind, I'm like pointing at my phone as if you could see it. But remind is a much quicker because then I don't get this delay. All right. Anyway, actually, well, it doesn't matter. Either way is perfectly fine. I'm seeing both. All right. Charge per second is known as charge per second. That's a little bit deep in the weeds here, but charge per second is talking about how many charges like in a wire. So here's a wire. Woo, okay, I didn't mean to go diagonal, but I did. The charges going by in a second through the wire. If you were to count them as they move by, what do you call that? Well, that is there's basically 3 choices. Over here ever with these things. It's basically current, voltage, and resistance. Okay, so which one best fits that? Is it the flow of electrons, current? Is it the push, called voltage? Or is it the opposition to flow, called resistance? Well, if you're talking about charge per second, that sounds an awful lot like flow. How many things are going by you per second? So the answer is current. Okay, so when you get a question like this and you're just not sure, or maybe you have to make an educated guess, or maybe you're like second and third and fourth guessing yourself, just remember, well, there's power too. Power is the same as power as it was earlier, but so it's basically 3 or 4 things. Okay, the flow, current, the push, voltage, the resistance, and then like the little cousin, power. That's just how much energy. Power is energy per second. All right, energy per second, not charge per second. Ooh, that actually can get confusing. So make sure you know charge per second. The charge is going by, just like picture the charges moving through the wire. The little electrons, that's current, okay? Energy per second would be power. How much energy is used up per second is power, all right? If you think like, wait a minute, we heard power before, that was in the energy unit. So that's kind of ways to keep those straight. And if you're writing stuff down, which you definitely should, that's something you could write down. I don't think I'm gonna ask this question, but, so I'll write it here. Power is energy per second. Okay. So if you remember back from, of course, from January, P is, well, how did we say it? It was work divided by time, and work is energy. There's other ways to do it. But anyway, so that was just to... I only say that to compare it to current charge per second. Okay. Which of these makes a good insulator? Choose more than one. All right, so insulator versus conductor. So versus conductor. All right, insulation. What does insulation do? If you know insulation in terms of heat, great. That is perfect, because what does insulation do? It stops heat or cold or something from moving into another place. Insulation keeps your house cold or cool in the summer and keeps your house warm in the winter. It stops stuff. It stops heat flow. Okay. Insulators, in terms of electricity, stop charge flow, the flow of charge. And so, okay, versus a conductor, which is something through which charges easily move. Okay. So remember, conductors are any types of metals, watery things, not pure water, but just watery things will allow electrons to move, conductors. So, but that's not what it's asking. It's asking which is an insulator. Well, copper is a good conductor. It's a metal. Okay. Remember this too. If you're ever not sure about something like this, like for example, maybe you didn't know what copper was. Okay. I mean, I think you do, but maybe you didn't. You call me over, Mr. Jern, what's copper? And guess what I would say? I would say it's a metal. Okay. It's a type of metal. That should be your clue. Mr. Jern, what's rubber? Okay, I can tell you that is a springy non-metal type stuff, right? So I could tell you that kind of information. If you don't know, like well, all this stuff you probably know, but every once in a while it's like, well, what is molybdenum? It's like, call me over. I don't think that's on the test, but if you see something on the test, so gold is a metal, aluminum is a metal, glass, that's a resistor, and plastic is a resistor. So anything that's not a metal, it's safe to say it's going to be a resistor. Plastic, glass, rubber, PVC stuff, what do you call it? Polystyrene, I almost said styrofoam. That white stuff, the white styrofoam. We all know what styrofoam is. Okay, so if you're ever not sure, if you just don't know what something is, call me over. Bink. All right, now assuming these are wires, which wire would have the most resistance? Okay, now whenever I ask this question, our brain tends to flip-flop things. Okay, it's like, wait, the most resistance means it's going to have a little more resistance means less current, like our brain wants to conflate. That means put two things that are unrelated together. Our brain wants to confuse, we'll just say. We say the word more. We feel like more resistance should be more. Okay, so to be clear, more resistance is going to have less current. You had to think it for a second. I mean, it's obvious when you think about it, but you have to actually take a second and just like, hang on. Okay, focus. And okay, most resistance. Most resistance is going to be, let's see, most resistance is long. This is straight from the notes, by the way. Thin wire. Okay, long and thin wire. Okay, remember I passed around those thick wires because, yeah. So that means letter A is going to have the most resistance because it's longer and it's thicker than the others. Okay. B is longer, but it's, hang on. A is thinner, sorry. B is longer, but it's thicker. And so it's going to have a little bit less resistance than A. Let's see. C and D are both short. So they're going to have less resistance because they're short, but yeah, if you're looking at long, thin, so what's the opposite of that? We'll have less resistance. All right, I'm over explaining. I apologize. Look at what I wrote. Most resistance, long, thin. Less resistance, short, thick wire. I like to over explain. You know that. I apologize. All right, series or parallel. There was only one pathway for the electrons to flow. You don't have to put it in the chat because honestly, like I said, with the delay, unfortunately, I just don't see it until like, I think there's like a 10 or 15 second delay. And that goes both ways. Okay, series or parallel. So you answer this question to yourself. One pathway. One pathway. All right, that is basically the definition of series. Okay. Multiple pathways is the definition of parallel. One pathway is the definition of series. So series or parallel. When a new bulb is added, the other bulbs get dimmer. Okay, we did that FET simulation. I didn't add it to this. I could have, but I thought, yeah. Well, is that it? Okay. And yes, either. Oh no. Is it going to ever be either? It might be. Not this time though. Series. Because when you add more, so here's like a basic, ooh, that's a terrible symbol for a light bulb. So let's say you have like a happy little circuit with a single bulb. And so this offers some resistance. So some resistance. Now it's like, hey, wait a minute, let's add another bulb right here. And now we have some other resistance. We just increase the total resistance. What does resistance do? Everything has resistance, by the way. Resistance slows down, it opposes current. So that's why they get dimmer. It slows the whole thing down. Series or parallel, each resistor has the same voltage as the total voltage. There's only one way this happens. And as you saw from the combination circuits, it's not like necessarily every resistor, it's every branch. So, but this could happen in some of the early practices. And so that's parallel. That's the only way that's possible. It is possible, but the only way it's possible is if they're in parallel with each other. They're wired in parallel. When one bulb goes out, the others remain on. How is that possible? How's he gonna draw this? I'm not good at drawing, but most of us aren't if we're doing it really quickly, which I am. So if I were to, for example, take this bulb away, there is still a path for the electrons to go. And that is so parallel. That's parallel. Okay. One way, one bulb goes out, they all stay on, or the other ones stay on. It's parallel. And by the way, with the delay, if you ever need me to go back, I can. Let's go back to another question. The current through each resistor is the same. The current through each resistor is the same. That's tricky. I don't like how I worded that question. I don't like how I worded it. Tell you what, I'm going to add the word always. There we go. Always the same. The current through each resistor, is always the same. Yes. Okay, now it's not as ambiguous. It was too vague a question. Now it's much better. In every situation where this is the case, it's either series, parallel, or either the current is always going to be the same. That is series. Okay. I had to write the word always because it's definitely possible. If the resistors are the same in parallel, then they're going to have the same current. But always the same, no matter what the resistor is. If they're wired in series, they're going to have the same current. One more. They can have switches. They can have a switch that turns off some lights, but not others. Okay. Hopefully, this stuff is fairly obvious, and you're to the point where it's like, okay, you remember it. Hopefully, you're feeling that, like, oh yeah, we did this stuff before spring break, right? And you're like, okay, good. We got all this. So we have a switch. Let's just not make this a switch. So this is an example of this. Right now, if the switch is open, like it is showing, this light bulb can be on, and this one will not be. Okay. If I close the switch, then this one could turn on. So parallel. That's the only way. None of my choices were either, especially since I fixed that one. So these are fantastic multiple choice questions for tests. Okay, now this, you may have to be prepared to do a memory wipe because this one this animation here is, instead of saying electrical potential energy, it's replacing the word electrical with gravitational. And so essentially that's what's going on here. The battery, which acts like a pump, instead of increasing the pressure, another way to think of it is that it increases the potential energy. It's electrical potential energy, but this is showing it as increasing the gravitational potential energy. And so that's what a battery or a pump does, is it raises the energy. That's all it does. And so you get this, like, these things kind of roll down a little bit. There's a little bit of resistance in the wire, I guess. And then it's showing that the electrons are, as it rolls down from high potential or high potential energy to low potential energy, that rolling just like a waterfall, just like a turbine, a water turbine in a hydroelectric dam, can be used to steal some of that energy and transfer some of it into some other kind of energy, kinetic, electrical, whatever you want to call it. All right, so I don't know if that's helpful. And so here we have one, and these two are the same. Here's that let's get rid of that and this. So here's that one from earlier. I turned it sideways, and then here's the same idea where, and this is maybe going to help. I don't know. And if not, you can just look away and just like sing really loud or something so you don't hear this. But so the battery increases the potential energy. And when things are wired in parallel to each other, this is why they're both at the same, they have the same voltage, because they're both these two would have the same voltage drop down them. This is why when they're wired in parallel, they have the same voltage, because they start out with the same high electric potential energy, in this case high gravitational potential energy, and they both are down to the zero, basically, essentially, or what we'd call zero. So anyway, I don't know if that helps visualize things or not. Here's another one. Once again, I gotta get rid of my drawings. Okay, don't go away. My phone just decided to go blink. So here is a 30 ohm resistor and a 10 ohm resistor. Even though they're both different resistances, this one's spinning a little bit slower. It's like, maybe it's like pushing more or something. I don't know. They both have the same voltage because they both start from the same high energy potential. So anyway, just another analogy to think about these things. Here's one when they're wired in series. Once again, let me just erase my previous mess. I guess I could use like the laser beam. So once again, low potential, high potential. And these ones are wired in series, which is why when you're figuring out those series ones, they have a different voltage, because they add up to the total. Okay, it's just like you go down a little bit and then you go down the rest of the way. Again, just analogies to help you out a little bit. So this one's a little complicated. This is what we're all about. So this one is a combination, high potential, and then going from this little corner where they have the choice, this one branch to the left has two resistors wired in series, and they have the same voltage as this R3 over here that's wired in parallel with these two over here. It starts from the same height, they fall to the same bottom. Okay, high potential, high pressure, high voltage, whatever you want to call it, low pressure, low voltage, whatever you want to call it. All right. So another question, final question for 7.1. Again, hopefully those are just analogies, not test questions, just helping to visualize this. This is a little abstract, so visualizations and analogies are all we've got, unless you just want to stick to the numbers, which is perfectly fine. So why can squirrels, is this meant to go away? Anyway, why can squirrels and birds and stuff land on high voltage or stand on high voltage power lines and not die? Well, the reason being is because if you're standing here, it's like there's no reason for it to go through you. But if you stand with like 1 foot here and 1 foot here, these charges aren't falling down here. They're going through a wire, and now you're a new wire in which it's going to use you as a ramp to roll down through your body to get to the bottom. Okay, so to answer the question is, why can squirrels and birds and stuff stand on high voltage power lines? Because there's no potential difference between their feet. It's like 1 foot here and 1 foot here. It's the same pressure. There's no difference. There's no reason for it to roll down. It's going to take the path of least resistance, these charges, and going through the squirrel's body or the bird's body is not the path of least resistance. Okay, so if you're standing on a high, I don't recommend this. In fact, please don't do this. And people who work on high powered lines, they do it. There's videos you can find on YouTube, high voltage lines, but there's all these safety procedures they have to follow. So don't take this lightly. I mean, birds do it without thinking about it, but every once in a while you'll see, you know what, I'm not even gonna bring it up. So that's the answer. Both feet are, there was a quiz question about that, and there's probably gonna be a test question about the same idea. Any questions about circuits? Now we're gonna get into Ohm's law and all that in a moment. So any of the math stuff is coming up. Okay. If you do have any, put it in there. I'll talk to you. Okay. What is the resistance? All right, this was a quiz question, right? It was on the recent quiz. Laser? Pen. Resistance when you have a graph of voltage versus current. Well, resistance equals the slope. Okay. So I'll take two dots, preferably on the line. Here's one. We'll go with this one right here. This is a little tricky. So this is, I don't know, 0.9. We'll call it 0.9. Comma. It's pretty close to 1. Let's just call it 1. All right. We'll deal with that. This does look like it goes through 0, 0. So I'm going to actually choose 0, 0. Whenever you can, use 0, 0. Okay. So, all right. So slope y2 minus y1 over x2 minus x1, x1. Why am I writing diagonally? I don't know. Let's see if I could tilt this thing a little bit. All right, so y2, so I like to do this, x2, y2, and this is my x1, y1. So let's do y1, 1 minus 0, divided by 0.9, let's go 0.9 just for clarity, minus 0. So it's 1 over 0.9. So my slope is 1 over 0.9. 1.111111. So 1.111111. So my answer is going to be C. Okay. So the slope is on the equation sheet. Where's it at? So in case you forget, oh, it's nice if I click over here. Somewhere on here, it's, if you need me to find it, there it is. Okay. So slope right there. All right. Let's see if I can bring that other screen back up. That was kind of, well, it was planned. Okay, good, cool. All right, slope is resistance when you have a voltage versus current graph. How much current would there be if voltage was 5 volts? Okay, well, 5 volts. So let's just go to our little graph, voltage right here. Oh, it only goes up to 1. So you might be tempted to choose letter D. However, we did just figure out that resistance is equal to 1.1 ohms. So we can use Ohm's law, I equals V over R, to figure this out. So if there's 5 volts and we know that the resistance is 1.1 ohms, well then it looks like it's gonna be close to 5, I'm guessing. Let's just divide that in our calculator. 5 divided by 1.1. Oh, it's not. It's not 5, and I should do that. I should have known that because the answer I got, so let me just erase this really quick before I get anybody confused. The answer I got was, what did I get? Here, I can show you what I got. Doesn't really matter, but I'm going to put it up there anyway. There it is. So 4.5. So yeah, the answer is A. Okay, that right there is an example of why to not rush through problems. All right, I'm like, whoa, 5 divided by 1 is 5, so it must be pretty close. Yeah, it was kind of close, but it was closer to this choice than it was to my other choice. All right, so take your time, do everything right. All right, what is I? Remember, don't forget the easy stuff. I is current. Okay. You know what? I'm going to run into problems here because let's just do it this way. So I is current. Put that there. Now you know why I didn't want to circle it. What is A? A, what? What is A? Think about it. Oh wait, A is amps. That is the measurement, the unit of measurement of current. What is V? Voltage. What is R? Resistance. What is P? Oh, it's the very first thing we did on the that you should have done on the review guide, right? What is that? That's omega. It's omega. It's a Greek letter, omega. Omega. That is the measurement of resistance, which hopefully you have a ton of experience with. Same thing with W, watts for power. Wow. Power. Okay. So unused is E charge, because if you remember, charge was Q, but that's not on here at all. So just saying hi from, the before times. Okay. How to solve for current. They all look right, kind of. But hopefully your experience leads you to remember it's B. And if your experience doesn't lead you to remember it's B, it's on the equation sheet. All right. And so I boom, where'd it go? There it is. I equals V divided by R. All right. Cool. Berg. Go. Okay. Now you're going to see some questions like this. Real life type things. A pool filter rated for 1,119 watts draws 5.1 amps of current. Okay, real life situation. Literally, I looked. How much voltage is required? Well, Mr. Jern, what? Actually, come to think of it. Yeah, all right, there is another equation. So these are the two we're going to be using. We could have talked about these other ones, but they're not on the test. And yeah, reasons. So the one I have highlighted and this one are going to be the two that we're going to be really focusing on, right? So P equals I times V. That is the equation. So I can do, okay, watts is power. So P is equal to 1119 watts. It says it's got 5 points. So that's current, 5.1 amps. And we want to know how much voltage is required. So voltage is my question mark. That's a question mark. So I start with P equals I times V. And I want to rearrange that to solve for voltage. I almost said velocity. So I'm going to divide that by I to get rid of that. Cancels out. And whatever I do to one side, I have to do to the other. And so I almost multiplied. So I'm going to say V voltage is equal to P divided by I. Okay, so a little bit of algebra, no problem, right? So voltage is P, which is 1119 watts, divided by 5.1 amps. And so, I don't think you need to see this one, so I'm just going to do it, clear. 1119 divided by 5.1, yeah, 219.4. That's pretty close. So I got, I'll write down what I got, 219.4. It's volts. All right. The closest one is going to be letter B. Okay. 219.4. Pick the one that's closest. If you're not sure, call me over. Aha, finally. Now we're getting into the good stuff, right? This is the stuff that's scary. This is all the other stuff was just as important. Don't forget, if it's a multiple choice question, they're all worth 1 point. That said, I might ask, what's the voltage across the 15 ohm resistor? What's the current going through the 15 ohm resistor? Like there's a couple questions I could ask, very similar to the quiz, right? Where there's one circuit, you just solve the whole thing, and then there's gonna be like a few questions about it. Very, very easy possibility, okay? Now what I could do, and I probably should do, for questions that I think there's gonna be more than one, for circuits where there's gonna be more than one question, is I would actually set up the VERP chart, okay, and charts are good and bad. They're helpful, and so I'm just going to do like total 1, 2, and 3, and I could do this whole thing, bloop, 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 and it's ugly, but that's okay. Nobody's gonna see it but me, and anybody watching this video, but on your scratch paper, nobody's gonna see it but you. I don't know, well, I don't think I'm gonna provide the charts, unfortunately, but as you can see, it's easy to do. And if you wanna write the numbers in there, you can, just like they were in the practices. So the voltage across the 15 ohm resistor. My total voltage is 9. My resistors are 5, 10 ohms, and 15 ohms. Okay, now, total resistance. It's a series circuit. So I just add these up. And so I get 15 plus 10 plus 5 gives me 30 ohms. Okay. Now that I've got that, I can get this one. Oh, wait, okay, so I equals V over R, V equals I times R. I don't think I'm gonna need the other one, so I'm gonna leave that, I'll just write it because V divided by I. Okay, and then power, I'll write that if I need it, power. So I is V divided by R, so I'm gonna take 9 divided by 30. I don't think you need to see this, but I'm just gonna do it 9 divided by 30. So 0.3. Okay, 0.3. 0.3 amps. This is a series circuit, and so the current anywhere. So is the current anywhere? So we've got 0.30 amps coming out of here, which means that's gonna be the same current that goes through everything. So 0.3, 0.3, and 0.3 amps. Okay. I'm going too quick. There are videos. There's a video that's linked in the description to this video that you're watching right now on how to do it. I believe it's, well, actually I have the whole like chart playlist in there. And so in there is how to solve series circuits like this. Okay, now we want the voltage across the 15 ohm resistor. All right, so for now, I'm just gonna skip straight to the question I need. Voltage is I times R. So I'm gonna multiply 0.3 times 15, and you don't need to see this, so 0.3 times 15, 4.5, 4.5. Okay, 4.5 volts. So that's how you do it, okay? I recommend setting up the entire chart because it's way too easy to just think I'm going to just put in my calculator. It's a series circuit. It's easy, right? It's but you can see like there's a bunch of numbers I wrote down. There's a bunch of steps. Just take the time and do it. Okay, it's a series, which if you've been keeping up with the practice, this is one of the easy ones, right? Don't shoot yourself in the foot and screw up an easy one. All right, I won't say, you know what, a relatively easy one. All right, relatively easy. It's easier than some of the other questions, right? So take a minute, do it right, set it up. All right, what's the total resistance? What's the total current? What's the current going through the 15 ohm resistor again? Okay, once again, let's set up our thing. I notice it's not asking about power. I could, you know what? Honestly, I should do power just to make sure I did this right. Okay, if you have a moment. So this is one of those things, okay, how do I put this? Strategize when you're taking a test, okay? Get to this point, and then if you want to check it right away, you can, but maybe you should move on, because if you feel like, okay, I think I did everything right, it looks reasonable, especially if it's a multiple choice question and you got 4.5, and it's like, hey, there's 4.5 right there, you could probably move on. But if you have time, you can use power. Power wheels. These should add up to equal the total, right? Okay, so you can always check with power, and if they don't, then something went wrong. And it's a test, so I can't help you. Something's wrong. I forgot I. Okay. I, R, and we'll put power in there. Probably not going to use it at this time, unless there's some serious issues going on. Okay, but keep it there. It just, you know, just keep it in your back pocket just in case you need it. So total 1, 2, and 3. Okay, and that's what you want to do. Throw together a quick chart just like you've been doing and go from there. So the total voltage once again is 9. I've got 15 ohms, and get used to keep writing the units. Okay, it helps you keep things straight. Otherwise, you just got a bunch of numbers, a big pile of numbers. All right, now the total resistance. This is what okay, wait, hang on. So I'm going to write I equals V divided by R. V equals I times R. And R is equal to V divided by I. Okay, and then P equals IV, in case you were wondering. But star by the ones that are on the, that's not a star, that's come on, asterisk. These are the ones that are on the equation sheet. That's a horrible asterisk. I should have just wrote an arrow. Okay, so they're on the equation sheet. And total resistance. To quickly review, once again, there is an entire video. It's like 5, 6, 7 minutes long in the description right now. Well, not directly, but to the playlist where you'll find parallel circuits. Okay, it's relatively easy. Once again, the hardest part is this total resistance. All right, so the total resistance, and here I am gonna put the calculator back up. How much can the total power be off by? That is a fantastic question. All right, I will actually pause and answer that question. Let's do this one real quick. You just kind of got to be reasonable here, right? Let's do it for the next one. If the total power is in the hundreds and you're off by like 5, you probably are correct. If the total power is 10 and you're off by 5, you're probably wrong. Okay, so you have to kind of like think in terms of like the percentage of the actual size, because the reason you're going to be off, and you most likely are going to be a little off, is because, and you probably know this, is because of rounding. And when you're writing stuff down, there's just only so much room to write down numbers, so you have to truncate. You have to cut off some of the. You can't write down the entire number, so you're rounding throughout, and rounding throughout leads to rounding errors, rounding differences. And so you just kind of got to be reasonable, I guess. Like I said, if you're in the hundreds and you're off by 5, that's probably fine. But if you're in the tens and you're off by 5, that's something to question. However, if you're not sure, you make the call. Maybe put a star by it, flag that question, and come back to it later. Like maybe you feel there's like a 60% chance you got it right. Okay, cool. Look at the clock, see how much time you have, and move on, and then come back to it. Okay? So, great question, hard to answer. Like, there's not a specific number I could give you. Okay, so, oh, I just turned me off. I gotta turn on my other camera. There we go. Okay, now, if you didn't know, I stole one of the calculators from school. Don't tell anybody. But this button right here, I'm going to bring it back tomorrow. I just want to show you. This button right here is the button you want to use, the x to the -1. All right, I'm just wiggling it under there. Let's see if it'll focus. Ooh, almost did. Almost. X to the -1. That is your friend. So, I'm going to do 10. I'm going to turn it on first, and then I'm going to turn it on. There we go. On button. So 10, and I'm going to hit that inverse button. And then plus 5. I guess I'm going from the bottom up. Inverse, it doesn't matter. It's adding. Plus 15, inverse. Okay. Now, common mistake. You're in a hurry. That's your answer. You just got everything wrong after that. Because you got to get this part right, because everything follows from this. You have to, like, watch this. Just hit the inverse button again. Hit enter. That's my total resistance. You got to take the inverse of the sum of the inverses. So, and here, watch this. I'm going to round because 2.7. Okay, I'd feel weird if I didn't write the 4. 4, what the, Mr. Jern? Let's round correctly. How about 2.73? So I rounded, but I rounded to the hundredths. That should get me pretty okay answer. So to answer your question again, depending on how much you round, you're going to be off by a little bit. If I had rounded 2.7, I'll be off by a lot more at the end. So your call on how comfortable you are with the rounding. All right. When in doubt, put in an additional digit. So I was in doubt. I was feeling a little weird by leaving it off. It's probably going to be okay. Okay, what am I looking for? Total resistance. Ooh, question number 1 answered. It is 2.73. What is the current through the 15 ohm resistor? All right, well, now that I've got this, I can figure out so this is the resistance from the total resistance that the battery is pushing against, right? So I'm about to find out what is the current coming out of the battery. So current is V divided by R. So I'm going to take, my phone keeps wanting to go to sleep, and then I won't see anybody's reminds. V divided by 2.773. I got 3.2967. I'm going to have this in my hand as I write it because I want to see the calculator. 3.2967. I guess I'll round that to 3.30 amps. Okay. Now, one thing that I didn't do that I could have done right away is we've got an individual resistor all by itself right here, and another individual resistor all by itself right here, and another individual resistor all by itself right here. All of those, therefore, have 9 volts, 9 volts, 9 volts. Okay. So I didn't even need to do that, this current up here, because now I just want to know the current through the 15 ohm resistor. Well, hey, I could do that right here. I didn't even need to do this thing. I did this for fun. So current is voltage divided, so I go 9 volts divided by 15. I just wasted time. Now, if you're on a test, and I don't know, use your judgment how you want to proceed with this. So there's my answer. So I just found my answer right here. Okay. So that's the answer to the second question. I could be done now. And again, if I have time at the end, I could come back and finish it off, do all the powers, and decide if I wanted to retry that. So yeah, expect questions like this, multiple choice questions where I give you a circuit, another circuit, and I ask, a few questions about it. There might be more. There might be like 5 questions about it. I might ask, what's the current through the 5 and the 10? There's all sorts of questions that you could be asked about this. Last question. Of course, you'll see a question like this. All right, this is not anywhere near the level of the big ugly from the quiz, but it's a combination circuit, and it's not series, it's not parallel. So how do you do it? Well, we want to know the total resistance, and we want to know the current through R4. Okay, so we'll stay focused on that. And again, we might have time to add up all the powers and see if we're doing good, and I would love it if you did that. But we might not have time, and so you have to use your best judgment. All right, VERP. I completely and thoroughly enjoy being able to say VERP as many times as I do. It's fun. If you don't know what that means, it's okay. It's nothing really bad. But, all right, so total. Oh, wait, let's do this one. Holy cow, there's 5 of them? All right. And I can tell it's getting late. 1, 2, 3, 4, 5. Okay. So all of these, hopefully I don't need to fill in all of these, but I gotta make the whole chart just in case. And if you have your ID on you and you want to make straight lines, you can. I don't think the scratch paper is gonna have these pre-made for you, just fair warning. It was on the quiz to help you, but all right, just remember VERP. All right, so total voltage. I'm still going to write down everything. So total voltage is 50. These are nice and numbered, right? So R1 is definitely 20 ohms. R2 is definitely 15 ohms. This is definitely 10, 5, and 25 ohms. Okay. So now let's focus on getting that total resistance. It's the first question anyway. And this is pretty much our only place we can go to. So we look, we've got the 25, the battery, and the 1. So R1, R5, and the battery are all wired in series with each other. And they're wired in series with this whole mess of resistors here, which are all wired in parallel. So like I said in class, work your way from the inside out. We've got this circuit that's trying to be a series, but inside of it, we've got this parallel circuit. These things wired in parallel. So I'm going to take the inverse, 15, 10, and 5, because they're wired in parallel. So I'm going to, I'll write this down, I guess. 15 to negative 1 plus 10 to negative 1 plus 5 inverse, okay? And I'm gonna do the whole little thingy. Good thing I wrote that up there, otherwise I wouldn't be able to see what I'm doing. So 15 inverse, nope, not squared, plus 10 inverse plus 5 inverse, okay? And then that's not it. I gotta take the inverse of that. Okay, 2 points. That looks familiar. Oh yeah, because we just did that one. All right, 2.73 again. No, go away. Here we go. Wait, so oh yeah, it is the same one as that. So it's like I took this circuit, and I basically plopped it inside. That's why we got the same answer here. So what was the answer I got there for? 273. Okay, I'm gonna write that down, but I'm not gonna write it down to the top because it's not. That's not the total. That is the total resistance for this part right here, 2.73. That's unfortunate placement of the decimal place. So 2.73 is the resistance of all of this. Okay, all three of those together is 2.73 ohms. So now, if you count all three of those as one resistor, the equivalent resistance of the three of those together, you're just going to pretend for a moment that those three are acting together, because they kind of are. They're acting together, and they're acting together as a 2.73 ohm resistor. So unless I did something wrong, no, I didn't, because I got it right the first time. So we've got the 20, we've got now this 2.73 ohm resistor and the 25. So for the total resistance, I'm going to take 20 ohms plus the 25 on the bottom plus the 2.73 that I just got. And I don't trust I could do it in the calculator in my head, but I just don't trust myself. Plus 25, 47.73. 47.73. Yeah. Okay. Now, if this is getting long, I've got 2 videos, I think, in my playlist on how to do these types of things. So check those out. All right. Now that is my total resistance. Yes. One question done. What is the current through R4? What? Oh man. Okay. So I gotta figure this out. I don't care about the total current. Didn't ask me that. I don't care about any of the voltages yet. Okay. I don't think so anyway. There's a couple ways to do this. Okay. And depending on which class I showed you, I'm just gonna do it one way. If you know of other ways, it's fine. But it's math. Math works multiple ways sometimes. I want to know the current through R4. That's this right here. Okay. So what do I know? I know the total current going through all three of those. It gets split up somehow, which is part of the question I'm trying to answer. I know the current going through the equivalent resistance of the, I know the equivalent, the current going through all three of those basically, but they're 3 combined. And I want to figure out what's the current going through the one. Okay, I know the current going through the 3 combined is, no, I don't know that. Oh, yes, do I? Oh, no, I don't. I could figure that out right here. Let's do that. I could figure that out. So current is V divided by R. I'll just write the other as V equals I times R, and R equals V divided by I. Okay. So this current, this question mark right here, is what I'm going to try to figure out, because if I can figure out that current, then I'll know the current going through those resistors, what I was just trying to say. So I'm going to take 50 divided by 47.73, and I get which makes sense because it's kind of close to 50. 1.05 amps. So this question mark becomes 1.05 amps. 1.05 amps. That is the current running around that circuit. Okay, coming out of the battery, going through the R1, going through R5, and going through total R1, 2, and 3, or R2, 3, and 4. So I know that the current here is 1.05 amps. I know the resistance is 2.73 amps. When I have resistance and I have current, I can figure out voltage. Voltage is I times R. So I could take 1.05 amps times 2.73. Somebody wants people to look at them out there. I don't know why. Like, look at me, my loud car. 05 times 2.73. 2.866. So I'm going to round that to, so the voltage, 2.9 volts. Now, what the heck did I just find? I'm not 100% sure. All I know is that I had resistance, total resistance for these 3 resistors. I knew the current going through those 3 resistors was 1.05. I guess, did I just find the voltage through these 3 across these 3 resistors? Yeah, that's what I found. The voltage from here, from X marks the spot to X marks the spot, that is my 2.9 volts. How does that help me? Okay. Well, we found it. Now we got to think about it. Well, remember the trick about things wired in parallel. They all have the same voltage. That means that the voltage right here is 2.9 volts. Oh, wait a minute. We got voltage. We got resistance. We could divide. So I'm going to take voltage is 2.9 volts. And sometimes you just go, it's like a puzzle piece. It's like, I don't know what this piece is, but it looks like it goes here. And then it goes there. And you're like, I don't know what that is. And then later on you find out, oh, that was like a bird's face or something. You know, it's like, sometimes you just don't know. V divided by R. R is 5 because it's this resistor right here. R4. And 2.9 divided by 5 gives me which R4. Okay, it's this one down here. 0.58 amps. Done. Done. I'm done with this question. Did I get it right? I think so. But if I've got 15 minutes left and I've got 10 more questions to go, I'm good enough for now. I'm gonna finish those and come back to this one if I have time, right? And maybe I'll figure out the rest of this chart and then solve for power. But this right here is worth 1 point. This right here is worth 1 point, right? Use your time wisely. All right. Know how to do this stuff, but don't give too much thought and time to any one question. All right. In fact, I would recommend leaving these questions to last anyway, if you can, because they take up so much time. So I think that's about it. Any questions? I'll put this one back up, but that is it. So use the time wisely that you have. That's right. Looking at the remind. Okay. The test isn't until Tuesday. Today is Sunday. Look at the playlist that's in the description to this video. See if any of those videos might be helpful to you. And can you do 23? Oh, probably. Guess what I did not prepare for? Let me open that up. The guide. You would have thought I would have prepared for this. Unit 7 review. Okay. Number 23. I can attempt it. Oh, is that the one about you accidentally hook up a 9-volt battery to your flashlight? Yeah. Okay. Let me see something really quick. Bloop, 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 bloop. Okay. So here's what I'm going to do. Let me just do one of these things. I'm going to plop this into slideshow. Maybe. Next. There we go. Okay. So now I could solve it for you. This is the one. If it is not the one, stop me, but I think this is the one. It literally says 23, so of course it's the one. Okay. How many flashlight draws? Okay, how much current goes through your okay, there's a couple ways to do this. 9-volt battery. Okay. You could do it two ways. One is you could do it as a two-part problem. So normally your flashlight takes equals 1.5 volts. Normally your flashlight draws 3 amps. That's a very powerful flashlight. 3 amps. And so the first part you could do is just figure out the resistance of your flashlight. And so R is equal to V divided by I. Yes, I've written that down several times, so I know that off the top of my head. And so 1.5 volts divided by 3 amps, right? So R is, is that 0.5 divided by 3? It is 0.5. 5 ohms. Why did I do that? All right, well, now we're going to plug it into our 9-volt battery, and we're going to figure out how much current goes through it, because now V is equal to 9 volts. So, and the resistance of your flashlight doesn't change. It's 0.5 ohms. And so we wanted to calculate the current. All right, I equal to V times R. So let's just plug those in. Volts is 9 volts. You can kind of see where I'm going with this, right? 0.5 ohms. And so R is equal to 4.5. Okay, going too fast. I is equal to 4.5 amps. Okay, your flashlight is used to drawing 3 amps. It is now drawing 4.5 amps. That's going to probably burn your flashlight out. It's the wires are designed to only carry so much current. Okay, it's like fire hose pressure going through a garden hose. It's going to break something. Something's going to break. That's how you do it. So what's going to happen to it? It's going to break. It's going to burn out. It's going to probably not start on fire, but it'll overheat and it'll be fried. The second way to do it is you could just think of it as a ratio. Okay. 1.5 volts gives me 3 amps. I don't know why I put the decimal point there. And so what about 9 volts? Is going to be X amps. And so 3 times 9 is what, 27? I cross multiply, 1.5x. Hope this works. So if I divide 27 divided by 1.5, hope I get the same answer. I didn't. I got 18. Something's wrong. Maybe you should do it the first way. I somehow screwed this other one up. Volt amps. What did I do wrong? Not like screwing this up on a live. Resistance 1.5. Okay, current. Resistance is V divided by I. Did I do this wrong? 1.5. 3 times. Yeah, something's up. Where did I make the mistake? This is why you write everything down, by the way. I could open up the key and sort of cheat. In fact, that's what I'm going to do because my head's not in the right spot right now. Verb combo key, electrical circuit. Oh, that's the key. That's the test key. I don't want to do that. You said exam, answer key. Nope. Review key. Now let's see that. No. Did I not finish it? All right. Well, 1.5 volts, 3 amps. Resistance is voltage divided by current. Voltage divided by current. Yep. I initially did the ratio and got 18 too. Maybe the ratio is not the best way to do it, but it should work. So I feel like something I got wrong here. The resistance is 0.5 ohms. I equals. I would just stick to the first way. Bottom line is you're going to get more current than you. At least the first way you could see, like I'm looking right now. And you get to see flustered Mr. Jern here. That's great. I equals V times R. 4.5. Well, somehow the math is not working out. So I'll tell you what, if you want a little extra credit, the first person to message me with the problem, I will gladly take it. So it's all written down there for you. Something I did wrong. I don't even know what I did wrong. But I'm not, yeah, somebody else is agreeing with me on here. Well, this is gonna bother me. Does anybody else have any other questions? Because if not, you can leave, unless you want to see me like study this for a minute, which I'm going to do. Okay, voltage 1.5. Just double check everything. This is what you gotta do, right? Current 3 amps. Resistance is voltage divided by current. That's not where I made the mistake, right? No. So 1.5 divided by 3, 0.5 resistance. Seems right to me. All right, so the voltage is now 9 volts. That is, all right, 9 divided by 1.5, that is 6 times more. Well, I'm going to leave this up to you guys. I suggest using it this way because then you could look at it to answer your question. This is how I would do it. But I'm missing something, and for some reason, just like happens to everybody, my brain is just not finding what I'm missing. So point it out to me, and you'll get some bonus points. All right, whoever does it first and correctly. What am I missing? What are we missing here? So I'll hang out for another, I'm going to do this for like another minute, and then this is not really super engaging YouTube live stream, so watching me solve puzzles, that should be fairly straightforward. Voltage is 9 volts. Yes. After this, can you show how you deciphered 16? Oh, this depends what it is. So yes, probably. All right. I equals V. Oh, wait. Oh, this is it. It's not. It's okay. This is it. Oh, yes. Okay. I got a couple people answered me. This is wrong. This is why you write stuff down, and this is why you don't get complacent. I equals V divided by R. All of this is wrong. Haha. All right, cool. We all thought of it at the same time. That's so cool. This is why you write stuff down. And you think I just do this on purpose where I mess up just to see who's paying attention. And I don't. I really do mess up sometimes. We all do. And that's okay. Just try not to do it live on a live stream when you're doing a review. However, I think the lesson here is learned. So this is not correct. It is 18. And so this is also correct. So you can do it either way. No, you get, somebody's like, wait, I don't have extra credit. Yes, you get the extra credit. Okay, you get the extra credit. So don't worry about it. You got it right as I was getting it to. All right, so very good, very good. All right, cool. So once again, this is why you write stuff down, right? You could go back and like, hang on, something about that didn't work out. Hopefully you don't make the mistake in the first place, but yeah, there it is. All right, you want question 16. Let's do this. Draw a circuit diagram for the circuit below. Yeah, I could do that. Just yeah, no problem. All right, let me just get a little screen grab of that as well. And you know, I'll grab these things too. And then I'll pop it into a new slide so I could draw on it. All right. Great question. Well, I don't know if it's a great question, but you had a great question. All right, so. All right. This one, right? If it's not, say something or forever hold your peace. At least you won't be the most awkward person on the internet this time. That is reserved for this guy. All right, you want number 16, draw a diagram. Okay, so yes, how do I do this kind of stuff? Well, I start with the battery, or it's a cell, but I'm just gonna draw. Okay, let's just kind of do like the little thing. Start it off that way. And you know what? This might be my first draft, and maybe okay, 17, sure. You know what? And yeah, ask the questions. That's why I'm doing this, right? So I'm going to follow it along. So I just kind of did this, and now I'm going to try to draw this, but I'm going to make it a little bit like more perpendicular. And then I'm going to get to right here, this part right there. This is a little like confusing looking, but basically what's happening is there's a choice of electrons. It could either go down this way, or it could go up through the battery. So I'm going to emphasize that choice of paths by actually extending out a wire like that. And then it goes down through another battery or wire. Light bulb. What time is it? And all right, now since this second one, okay, so this is A. B, and then going back to the battery seems a little straightforward. So I'm going to leave that till last because I might need some more room down here. And again, this might be my first draft, and I need to like redo this. So I'm going to come out now. Same thing's coming out here. Like it's coming out of the light bulb, and there's an immediate in this diagram split, choice, path, whatever you want to call it. It could go either toward C or toward D. All right. So I'm going to do that again. I'm going to do a little split, make them perpendicular to each other. And I'm going to head down toward C right here. Okay, so this will be C. And this right here is just like, that's just there to confuse you. In fact, that doesn't make me sad. That makes me angry. Is that angry? Those are angry eyes? There we go. Now I'm looking angry. Okay, like what is even? That's just, you don't even draw that. Okay, now, on the other hand, I could put this light bulb here, but I kind of see where this is going. It's going to like loop back around and join up wherever C's been. So I'm going to do this, and I could have just put it up here, it doesn't matter. And I'm going to come back around, and it looks like that might even be it. Is that it? Okay. I know I've done this before because I assume this is in the key. So they come back. This is my thought process. You're just seeing me thinking about this. I have not thought about this in a long time, weeks maybe, since I made the key. So you're watching me do this kind of raw. So now it comes back together, and we get this point. That's what this is right here. Okay. And now after that, there is a switch. So I'm going to draw the switch. Okay. And then it's going to come back, this switch right here. After the switch, it's going to come back, and after B, it's going to come down together, and the switch and whatever B was at is going to come together. And right here is what I just drew, like this part right here. And then from that little corner, it's going to go through another switch and then back to the battery. So that's basically where I'm going with this. Okay. So then I'm going to look at this. I'm going to step back, and I'm going to be like, okay, did that make sense? I'm a physics teacher. I've had like a lot of experience with this. So, okay, it looks pretty okay. Like things are straight lines, perpendicular corners, all that good stuff, 90-degree corners. I guess that's an okay drawing. Like in fact, I would love that. That is if you do this, I would consider that a beautiful drawing. Okay. That is great. It looks fine. You did great. All right. So if it was me, I'm kind of a perfectionist, and I'm not on a time crunch for my test. So in fact, I'm trying to rush through this to, so that you could go to do what else you got to do. And I could go tell that person outside to get off my lawn, because that's what I do. No, he's not on my lawn. Okay. So hopefully that answers your question. 17 you want. Can I get 17 while you're at it? That's it for me. Okay. Rank them from brightest to dimmest if both switches are closed. Okay, so we're going to assume that both switches are closed now. And so the circuit is complete. All right, now, this is a little trickier, right? And you got to think of in terms of resistance. All right. B is going to be the brightest. So I'm going to immediately rank that number 1. Why? Because there is a direct path from the battery through B and back again. And it doesn't have to go through any of that nonsense. Yes, both of you get the extra credit since you both literally answered me at the same time. Direct path. No other nonsense of resistance or anything like that. Okay. Then, from brightest to dimmest. C and D are going to be the same because they're parallel to each other. A. Okay, now bear with me here. Pen. The current. And we're assuming everything is the same resistance, by the way. I don't know if that was said. We've got, let's just say, I don't know. No, I'm not even going to make up numbers because that's not cool. Like I said, unfettered, one resistor, one light bulb that direction. That's why it's the brightest. There are 3 light bulbs going in this direction, and they're in kind of series with each other. A is in series with C and D. That's not good. That's more resistance than what B is getting. So that's why B is the brightest. So B is the brightest. Then comes A. A is next. Why is A next? And then I'll put C and D because actually C and D are equal to each other. Okay. So why? Why is it like this? But they're last. All right. For real. I don't know if you guys are hearing that. It's just a little distracting to me. Here's why. Let's just say you get this nice amount of current going through this wire right here, right? What happens to that current? And you get like tons of current going down here, right? And like all this current coming out of the battery, right? So I'm just going to represent this with some really horrible lines. All this current going this way. Some current going this way. Well, that some current going this way has to get divided up now. Some of it's going to go down this way and some of it's going to go down this way. And so more current means more brightness. B has the most current because it has the least resistance. A has basically the sum of whatever D and C are getting together. And so it's going to be, I mean, effectively as bright as C and D together, maybe, because it has all that current going through it. So that's why I got the answer I got. Okay. If there were numbers, it might be easier, but can I give numbers here? You could assign numbers to this. If you want to do it mathematically, honestly, you could. You could say, well, this is 50 volts. You make these all 10 ohms, okay, as long as they're all the same. You could probably verify that if you wanted to do it mathematically. You could figure out the current. If you figure out the current, you have figured out the brightness. More current means more brightness. Okay? Anything else? Fantastic questions. So in class tomorrow, I'll answer more questions that you might have. And study wisely, and then be prepared to take the test wisely. All right. And I'm just going to reiterate: don't forget the easy stuff from before. All right. These kind of questions. Spend the time on it. Try to understand it, of course. Okay. But then when it comes down to it, these are only some of the questions. There's other questions. All right. All right. Well then, you guys have a fantastic evening. Enjoy your last couple hours of Sunday. And I will see you tomorrow. So take care.